In this screencast, we'll talk about how to use Newton's method to solve for scalar nonlinear algebraic equations. So, as with any solution method for nonlinear equations, it's an iterative method, which means you take an initial guess and then you try to update that initial guess intelligently until hopefully you converge onto the solution. So it is a method to solve the following type of equation, where you have f of x equals 0. So we have some function f, and it's a function of one variable x, and we're trying to find the value of x that makes f equal to 0. These values of x that make f equal to 0, they're called zeros of f. So let's go ahead and do a thought experiment about how we could potentially find zeros of f. So let's say that we have information about our function f at a particular point x0 or x0. So how could we approximate the value of f at another point, say x? So simply what we could do is we could do a Taylor series expansion. In a Taylor series expansion, you would have your approximation of f at a point x is equal to the value of x at x0, the value of f at x0. And if you just stop with this first order approximation, or the 0th order approximation here, then your approximation is that they are equal. But we know that's probably not true because you also have some sort of slope to f evaluated at x0. So you probably have, what you want to do in your Taylor series expansion is you'll have another term, f prime of x0 times h, where h is the distance in between x and x0. But in addition to having a slope, and so that approximation would put you here, but in addition to having a slope, the slope changes with x, and so you might have a slope changing, and so you might want another term in your Taylor series expansion, 1/2 f double prime of x0 times h squared. But the way that the slope changes over x might also itself change, and so you might need another term, 1/6 f triple prime evaluated at x0 times h cubed plus ... Of course, to make our lives much simpler, let's just consider up to the first derivative. So we're going to ignore the second derivative and higher terms like that, and we're just going to approximate f by the first derivative. And so our value of f at a different value of x, let's say x1, is approximately equal to the value of f at our original point, x0, plus the slope of f at x0 times the delta x in between, x1 minus x0. And so that's our Taylor series expansion. And what we've just done is we've just made an equation of a line going from x0 to x1 with a particular slope, and it goes a particular distance, x1 minus x0. And so this is our approximation of f at a value x1. But what we want to do is we want to find a 0 of f. So we want to find what value of x makes f equal to 0. So our next best guess for the value of x1 that makes this happen would be where this linear approximation itself hits 0. So where does the linear approximation hit 0? That's where the linear approximation is equal to 0. F of x0 plus f prime of x0 times x1 minus x0. So what we've done is we've extended out this line to give us the point where the line hits 0. And so what we want to do is find what value of x1 makes that line equal to 0. Well, we can just solve for x1. x1 is equal to x0 minus f of x0 divided by f prime of x0. And so if our equation actually is a line, then x1 is our solution. But since this line is just an approximation to f, then x1 is only an approximate solution, or an approximate 0. So because that itself is just an approximation, what we want to do is we want to improve our guess even more, and so we find x2. So we say x2 is equal to, and what we're going to do is we're going to use the same formula we have up here, except for now we're going to use x1 instead of x0. So x2 is x1 minus f of x1 divided by f prime of x1. In other words, we started with an initial guess x0. We used an approximation for a line to make an approximation, or a better solution, a better approximation to our solution. And we're going to use that another approximation to a line to get another approximate solution. And we can do this as many times as we want. And eventually, we get a more general formula. X of I plus 1 is equal to xi minus f of xi divided by f prime of xi. And so this is an iterative solution method to find a 0 for f. So you start with some initial guess, x0. You apply this formula and get a new guess, x1. You apply the formula again and get a new guess, x2, and you do it over and over and over again. Here's our general formula down here. And eventually what's going to happen is that you're going to converge onto a solution. This method does converge actually very rapidly. And so, because when you're close to a 0, the error actually gets squared with each step, and so the error becomes smaller and smaller and smaller. And so here is a graphical depiction of what just happened. So let's assume that we have some function f of x. And we don't actually know this. We don't know that this is what the curve f of x looks like. We just have some function. And that function has a value at xi and a slope at xi. And so we're just going to extend that line out to a point where that line hits 0, and that's our xi plus 1. Now that point itself has a slope, and so we'll have another guess. Now in this particular case, with this drawing, the guess after this is actually not very good, but the fact of the matter is that this method does actually usually converge pretty rapidly. So xi plus 1 is where tangent line at xi hits 0. So let's take a look at an example using Newton's method. So we want to use Newton's method to find a 0 of the function f of x equals e to the minus x quantity, and then that minus x. And we want to do this to a tolerance of 10 to the minus 6. Now I haven't told you how to look at the tolerance yet, or what you should do, how you should know when you can stop doing the iterations, but we'll cover that in the example. So first, in order to do this, let's go ahead and compute the derivative of f of x. So f prime of x is equal to the derivative of e to the minus x, so that's minus e to the minus x, and then the derivative of negative x, which is negative 1. So there's our derivative. So therefore, our formula for Newton's method will be xi plus 1 is equal to xi minus f of xi on top, so that's e to the minus xi divided by f prime of xi, or negative e to the minus xi minus 1. So there's our formula. Now taking initial guess of x equal to 5, how many steps is this going to take to converge onto the root with an acceptable tolerance? So to do that, what we're going to do is we're going to head over to an Excel file. So in this Excel file, we have the equation that we want to solve. F of x equals to this. We have our Newton's formula. And what we've done is I've set up the initial guess. So what I want to do here is, in this next box here, I'm going to type the formula for the next guess. So that formula for the next guess is going to be based on this formula that we just derived in these lecture notes. So that formula will be equal to xi minus f of xi, which is exp of negative xi minus xi again, and that divided by negative exp of negative xi minus 1. And so here's our initial guess, xi equal to 5, and our next iteration is 0.04. And that's iteration 0 because I equals 0. So this is x0 and this is x1. Now the difference between the two is just simply xi plus 1 minus xi, negative 4.959. So what do we do here? Well, this is xi plus 1 for this iteration, but that's equal to xi for the next iteration. So I'm just going to say in the next row, the xi is equal to the previous xi plus 1. At that point, this formula is going to be the same as it was before, just copied down. So I'm going to drag down 1. And now my new xi plus 1 is 0.509. And this iteration is equal to the previous iteration plus 1. And the difference is the same formula, just dragged down. So now I have a difference of 0.469. Okay, so that's 2 iterations, right? Or we started with x0, and then we got x1, which is here in 2 places, there and there. And now we have x2. And at this point, now that we've filled out our first 2 rows, we can just take this second row and drag down several rows. And what you can see is x2 is here and here, x3 is here and here, x4 is there and there, and at this point, x5 looks like it's the exact same value of x4. And in fact, when we look at our difference is 6.71 times 10 to the minus 8. So this value of this difference is so low that it's below the tolerance that we specified earlier in the problem. Because what we said earlier in the problem was that we wanted a tolerance of 10 to the minus 6. And so what that means is that it only took 4 iterations before we converged onto a 0 of f of x to the acceptable tolerance. The iterations that I provided after that were superfluous. We didn't need them, right? And so what you would report in your Excel file, you can keep those rows or you can delete them, is you can report that your solution is equal to xi plus 1 in the 5th row, which is the 4th iteration, which I guess is x5.